Professor Hanan. Professor Hanani. Hello. Hello.
Yeah.
Professor Hanani.
Yes. Good morning.
Assalamu alaikum. Welcome. Welcome.
Thank you very much.
Welcome.
Thank you.
Welcome, sir. Welcome.
Good. Nice to see you again. Nice to see you
After a
again.
long time. After a long time, sir. After a long time.
Because the last time it was in Malaysia.
Yeah, yes. Last time it was in Malaysia. Yes. Yes.
Yes.
I wanted, believe me, I wanted many times to have you here in Kashmir, but could not make it.
I know, it's finally something going on.
Yeah, I tried my best.
I think the sound's gone. The sound has gone.
Hello, Shasa? Shasa?
Yes, I am. Yes.
Sorry, sir.
I think
Actually, I was hoping that Shasa will also be with us. He's there, but I think there is some internet issue,
connection.
connectivity
Yeah.
issue. Yes, sir. Okay, sir. Let us start with your session.
Okay.
Good morning, according to UK, and good afternoon, according to India. Now, starting with our second session of day one, I would like to introduce our first speaker, Professor Mohamed Henani. Professor Mohamed Henani has an expertise in the physics and technology of molecular beam epitaxy growth for third to fifth electronic, optoelectronics, and spintronic devices. This sophisticated epitaxial growth technology, which is now commercially used to mass produce devices, is becoming increasingly important for the development of advanced and innovative semiconductor materials and the devices for the semiconductor photonics and electronic industry. It is worth mentioning that the attributions of several Nobel Prizes have been directly linked to the results obtained by molecular beam epitaxy grown samples. He has an established reputation and as a result collaboration with many scientists both in UK and overseas, including the 2010 Nobel laureate Professor A.K. Jim. He has been studying various aspects of lower dimensional semiconductor structures and devices grown by molecular beam epitaxy technique for over 25 years. During this time, a significant contribution to the understanding of physics underlying the operation of such structures and devices has been made. The research work he has been recognized nationally and internationally. Now, I would request Professor Henani to kindly start with this session. Nani, sir.
Okay. I've never used Webex. I will share my screen now, but I cannot share.
Sir, just a second.
You have to allow me to share the screen.
Yes, sir. Yes. Sir.
Yeah.
Press into it.
Okay, so let me just see now. Can share the screen. Can you see the screen? Can you see my screen? Let me just see. Share. So share content. Share screen. Just see and then
Yes, sir. Now it is started sharing.
we can start. Yeah. Okay. So let me just downloading the PowerPoint. So can you all see it?
Yes, sir.
Okay, let me just see pointer option, laser force. Okay, how can I get rid of this thing? Okay. Well, good morning, ladies and gentlemen. It's my pleasure to join you this morning or this afternoon in your time to give my presentation. So what I did, I'm trying to give practically an overview of what we call low-dimensional semiconductor structure and quantum devices, if you wish to. I think Professor Kumar has already touched a little bit on this in one of some slides, but I'm going to try to make it as simple as possible because I am not sure how, because actually, to be honest with you, each slide could be a lecture in itself. So, but what I'm going to try to give you just an overview of the field of low-dimensional semiconductor structures and devices. And I will, show you some principle fabrication and mainly as well their application. This is extremely important. Let me just see now. How can I move to the next slide? Okay. I don't know how to move to the next slide.
Not enough.
So just
Okay.
click. Yeah.
Yeah, it just takes time. So this is the outline of my talk. I will start with a general introduction, and I will practically give you what is the motivation of studying low-dimensional semiconductor structure. But as into the introduction, one of the most important techniques which has really made this low-dimensional structure possible is this molecular beam epitaxy. And I will show you the impact this technique has made both in terms of research and production, producing devices as a mass. But for this lecture, I will mainly concentrate on some achievement of molecular beam epitaxy, and probably the most well-known devices are the lasers, transistors, for example, which are the most important devices. So I will touch on some quantum well and quantum dot lasers and some transistors, which are extremely important. As you know, lasers and transistors are practically the foundation for both optoelectronics and electronics. But I will as well, discuss some new hot topics about new emerging semiconductors, which could be used actually for photovoltaics. That's what we call the fourth generation solar cell. Okay, so let me just start with this introduction. As you all know, practically the computer technology is the driving force behind making devices smaller and smaller and smaller. I'm just showing you here, for example, this is kind of a computer which used to use, an electronic valve. These are valve, triode, diode valves. These are really big, and this on each device, each element is one device. So you can see there's maybe 100, triodes in here. However, as you can understand, the integration of when the transistor came to life, semiconductor transistors, because these are all valves, they use filaments. When they come semiconductor devices, practically people have been managing to integrate them into a chip. So this is just showing you a chip in here, and this chip could contain millions and millions of transistors in this single chip. So I'll give you some example. And of course, when you start, going to these smaller and smaller devices, the classical physics is no longer suitable to model the laws of physics. So that's what we discuss, all these low-dimensional structures by using quantum physics. And this is very, very important. So you can see the integration has allowed us to make millions and millions of transistors practically in your fingertip. Oops, sorry. Okay, so let me just, I think probably this is one of the most, I think, important slide, I would say. This actually was by Paul Davies. He wrote this quotation here. He's a philosopher. And what he says, the 19th century was known as the machine age. The 20th century will go down in history as the information age. But he said he believed the 21st century would be the quantum age. This was in 1996. He said this. I would say now we are in the quantum age already, because most of the devices you're using, are based on a quantum phenomena. Whether you're using a laser, whether you're using a transistor in your mobile phone, whether you're using a light-emitting diode, solar cells, they are all based on some quantum phenomena. And this is, I would say, we are in the quantum age already, where a lot of devices are based on a quantum phenomena. Let's start with Moore's law. I'm sure some of you know Moore's, Gordon Moore. He's the founder of Intel, and every practically processor in most of these devices is actually from Intel. And of course, what Moore did, he predicted that was in 1965. That's over 40 years ago, nearly 50 years ago. He said every 4 years, when he first invented the integrated circuit, he predicted the transistor density will double every 18 months. So that means the integration, or how many devices you can put in a chip, will practically double every year and a half. And this is actually, his prediction was right. If you look here at this is the time scale, and this is the number of transistors, practically the number of transistors per chip. So maybe some of you cannot remember some of these processes, but some of you probably will remember the Pentium 4 and so on. But you can see this trend that the integration, as the number of transistors was only around 1,000 in the early 70s, now becomes over hundreds of millions of transistors in a single chip. So you can see how by making things smaller and smaller, you can integrate them and make a lot of devices in a single chip. So this prediction, of course, how far it can go, there are, of course, limitations, and we can discuss the limitations in some of your questions probably. This cannot go forever, of course. There are some real limitations, how much you can put in a chip, and how small we can make them practically. You just see, again, it's stuck. Sure, why it doesn't want to go to the
So
next
just
slide?
move the cursor for a bit.
To where?
So just move the cursor. Just,
Yeah.
and then you can click, then it will move.
Next. Okay, next. All right. So here you can see here, for example, why we need quantum mechanics. I'm gonna show you why we need quantum mechanics, because as you can see, more law, it's already in the mainstream electronics into region where quantum mechanics is very, very important, because the device becomes smaller and smaller, and therefore quantum mechanics play a big role. So now, when I was talking about these hundreds of millions of transistors, which you can integrate in a single chip, one of the major limitations, for example, of making these transistors, which I will discuss later, is this gate, because every transistors have got 3 terminals. That's what you call the source, the drain, and the gate. The gate allows you practically to control the flow of electrons between the source and the drain. And is how small can you make this gate? This is one of the terminals of the transistors. So usually now people have been achieving around 10 nanometers in size. So you can see we're already now in this region where quantum mechanics is very important, where classical mechanics is not anymore, you cannot apply it. And this is now where you have to use the wave-like quantum properties of electrons on this length scale. But if you can look at this diagram here, what does it mean when you make the devices smaller and smaller? That means the number of electrons becomes smaller and smaller. So you can see here, in a device probably will have nearly 10,000 electrons. This is just showing you here, some memory chip. And then as you make, the devices smaller and smaller, you practically expect a single electron device. And we already have a single electron devices already. But unfortunately, they don't work at ambient temperature. They have to work at very, very low temperature. But we can make nowadays a single electron transistor. So you can see how these things become smaller and smaller, and the number of electrons becomes smaller and smaller, and where quantum mechanics becomes very important. So what is the motivation, you see, of all these low dimensional structures? Is practically to shrink the devices. I will explain this in a bit. And there are two approaches to shrink the device that we will call the top down and the bottom up. So either you start from the bottom and you go up. So this is what we call, the growth of epitaxial growth technique. This is what when you grow the devices, you start from the bottom and you build up these structures as you go up in the y direction. And once you have done, then there is the top down. This will involve a lot of sample processing. This is making the devices, and then by using these processing techniques, you can shrink the devices to smaller and smaller devices. So this is mainly the reason why we want to make these devices smaller and smaller and get into the regime, the quantum regime. We want to see some new quantum effects. We want to study some new physics, because the physics in classical physics is different than quantum physics. And this is very important, this confinement is how to engineer, how to confine the charges, the electrons and the holes, to confine them in space as well. And the kind of structure we can use for these kind of devices, we can use quantum wires, and quantum dots. And I will show you all some example of these, how they are used, for example, in making some real devices, both in electronics and optoelectronics. Okay, let me just first, because I'm sure probably some of you who may be in some advanced courses, who do semiconductor courses, what does it mean, size quantization in real life and in quantum theory? This is not so. So let's just look, for example, as you know, every device you can think of is practically a p-n junction. Either it's a laser, or it's a diode, or it's a solar cell. It's always a p-n junction. Okay, so I'm just taking here, for example, what I call a double heterostructure laser structure. So what it does, it consists of a p region and an n region. This is for electrons, this is for holes, and this is actually the active layer, where the electrons and the holes will recombine to give you a photon. So imagine this, what we call a three-dimensional system, where this active region is about 1 micron. So in 1 micron, this is a very big. That means this is a three-dimensional system, which means, for example, the electrons or hole have three dimension of freedom. They can in X, Y, and Z. However, if you make this region physically smaller, say a few nanometers, as you can see here, so here you reduce the freedom of the electron. Here it becomes only two-dimensional, only along the plane. So you have restricted one motion, one degree of liberty for the electrons and the hole. And you do the same thing for the wire and for the quantum dots or the quantum boxes. Here in quantum box, what you call them zero-dimensional. That means, the electrons or the holes is practically inside the box. So he got a 0D freedom. So he's confined in all three dimensions. So this is the physical size. But what does it mean in terms of other properties of the semiconductors that we call the density of state as a function of energy is extremely important. So for this three-dimensional system, this is what the density of state looks like. Well, just let me talk about the conduction bond. It's the same for the valence bond. So that means this is very continuous. But the number of state available for the electrons are very small. It's just around this region. So here you can see the density of state is very small. That means the number of allowed state for the electrons or holes are very, very small. So that means you cannot put many electrons in these energy states. However, if we go to a quantum one, you can see already there is a staircase. So now you started having some finite, increasing this density of state as you go along. But when you go to quantum dots, this density of state becomes a delta function. That means it becomes huge. That means you can input many, electrons and hole both in the conduction bond and the valence bond. That means if you make a laser That means you increase the gain because you got a lot of state populated with electrons and holes. Then you got a lot of photons coming out of these lasers. That means you got a lot of you have increased the gain of the laser. So this is what they're expecting. That's what the theory tells us. If you reduce the dimension from 3D to 0D, that's what happens to density of state, which is very, very important. So let me just go to the next slide. So this shows you here the first patent in 1976 from the Bell Labs in the US. Of course, Bell Labs is a telecommunication company. So at that time, they had this patent, and they used actually the density of state as a function of energy. And they said if you can reduce the dimension of this semiconductor from 3-dimensional to 2-dimensional, 1-dimensional, they didn't know even about 0D at that time. They said that you can change the density of state, and they said that if you can change this density of state, you can exploit these states in order to increase or to improve the semiconductor lasers. This is extremely important. But of course, in 1976, there was no technique available to make these devices, 2D and 1D or 0D. So this was practically a patent who started the whole race to make these quantum devices, but there was no technique to fabricate this, what I call from the bottom up for the growth of these quantum well lasers or this heterostructure. So this is, I would say, as you can see, it's not long ago, started the race of making these devices, and that's what people start thinking, how can we make these thin films of a few nanometers or few angstrom? So let me just go back to this table, the Mendeleev table, the chemical table. And of course, you are all familiar with the group 4, which is, the silicon and germanium, which is a very important group 4 element for semiconductors. And silicon is mainly for microelectronics. That's what you call elemental semiconductors. But the group 3 and the group 5, that's, for example, gallium and arsenic, aluminum, arsenic, these group 5 are extremely important devices. Semiconductor 2, this is what you call the group 3, 5. But also you got the group 2 and 6. These are also some different semiconductors. We call the 2, 6. But for today, I will mainly concentrate on the group 3, 5, which are very important for high-speed electronics, optoelectronics devices. So this group 3, 5. Okay, so how can we make semiconductor heterostructures, as the patent tells us? So the patent says, heterostructures practically just make like a sandwich structure. You just put different semiconductors one on top of the other. This is just like sandwich structures. So here, for example, you can see I'm just using some elements from the group 3 and some elements from the group 5. So aluminum, arsenic, and they build them layer by layer. And then you have here gallium arsenide, gallium arsenide, and then I top it up with aluminum and arsenic. These are just layer by layer, atoms by atoms on the surface. But when you do this, you change the energy profile of the structure. So this is the physical structure, but this is the energy structure or profile of the device. So because aluminum arsenide has a very large energy bond gap compared to gallium arsenide, so this what by doing this sandwich structure, you form what we call a quantum well. As you can see, it's a well both for the electrons and for the holes. So this is the conduction bond, and this is the valence bond. And this just show you, for example, the values of this bond gap of these two semiconductors. So this is how we form these heterostructures. It's just practically putting materials one on top of the other, and then we can practically engineer this energy profile of the semiconductor. So what does it mean, for example, if you want to make a quantum well? Pardon me. So we just use two semiconductors with high energy bond gap, like this aluminum arsenide, aluminum gallium arsenide, and we sandwich, gallium arsenide between this layer, which has a low energy gap, and that's what we have this profile, energy profile, as a function of Z. This is Z. Now here going from this to that. So by doing this, now what you have, what we call this confined energy state. So now the electrons and the holes can only occupy well-defined energy states inside the quantum world. And of course, you know, the number of allowed energy states both in the conduction bond in the quantum world depend on the width of the quantum world and the height of the barrier. So you can have one, you can have two, you can have three, depending on your application. So you can, by changing the barrier height and the quantum world, you can change this energy state. And I'll probably show you some example. So this is what how we can create quantum worlds in the conduction bond and the valence bond, and how we can quantize this energy state both for the electrons and holes. So this is very important. So this heterostructure practically changed our world. You know, they revolutionized both electrical and optoelectronics devices. And of course, I'm just showing you the most popular one: light emitting diode, lasers, transistors. So these are components which are practically used on a daily basis. What they're using a laser pointer, what they're using a laser printer, you know, where you're using laser, you know, surgery, so on. Transistor, of course, you know how they are used. So I will touch on some of those in next few slides. So how we can create this heterostructure? So today I will only, you know, concentrate on this molecular beam epitaxy, but there are other techniques. This is what we call metal organic chemical vapor deposition technique. This is what, for example, Professor Kumar has got in his lab. I have in my lab this technique, molecular beam epitaxy. The difference between these two techniques is that one only use solid sources, like aluminum is aluminum metal, gallium is gallium metal, arsenic is arsenic metal. But in this technique, they use all kind of chemicals. For example, arsenic, they use arsine. Gallium, they got metal organic gallium, and so on. So they use, you know, so this is mainly chemical, and you know, and this is mainly solid. So it's just sublime. And this is what you do practically. You got usually, because these are very thin layers, so you use a substrate, and then you deposit this layer by layer, and you do whatever you like, which you know, according to what design and device you aim to achieve. Okay, so this is what I'm gonna explain now. So what is molecular epitaxy? This is one of the techniques which made a big difference. And as I said in my, you know, introduction, it has resulted in several Nobel Prizes by devices grown by this technique. So it's a very simple technique. So molecular beam epitaxy is no more than an evaporation technique, but this evaporation is made under ultra high vacuum conditions. So the kind of vacuum condition I'm talking about, if you think about the atmospheric, pressure, is about 960 torr, say 1000 torr. But here in this machine, the pressure is 10 minus 11 torr. So you see 1000 to 10 minus 11, that's about 10 to the 14 times smaller than what you get in atmosphere. That means you have practically no impurities or gases inside the chamber where the evaporation is going to take place. So that's what you get, very pure film. And the way you can, you know, form this solid structure, you just load this, what you call furnaces with aluminum, gallium, arsenic, for this to form this gallium, aluminum, and arsenic. And in front of each furnace, you got a mechanical shutter, so you can open it and close it. They are very fast acting shutters, so they open and close very fast. So these allow you to build the semiconductors, but pure semiconductors are not very useful, you see. So you need some dopant. You have to make them N-type and P-type. As I said, most of the devices are based on P-N junction. So in MBE, we use silicon atoms to make electrons, to make them N-type, and we use beryllium to make them P-type. So we can grow any structures we wish, and we can dope them N-type and P-type. So this is as simple as I could explain. So actually, this is in 1968. This is again in Bell Labs at Cho. Alfred Cho and his colleagues, you know, built this system, what we call molecular beam epitaxy. As you can see, it's just on the desktop, because they're trying to evaporate this entire kind of vacuum, but it was very, very crude, and the purity wasn't very, very good. So they were struggling to make very good devices. So as you can see, this is one of the research machines. First, as you can see, is very, very small, and it wasn't very good, but it was a start. So here you can see some real commercial machine. This started around, I would say, in the early 80s. So it was 1968 in Bell Labs. So actually, Alfred Cho did contribute to some of the design of one of the French machine. This machine it did contribute to this design. So actually, so this is about 12 years later. So there was at least 3 major companies. One in the US called, they changed name to is called Varian. One is called Reber in France. Sorry, this one is Reber in France. This one was VG in the UK. And there was one company in Japan. But this actually, I would say, Reber and VG and Varian were the 3 major at that time companies to make this device. But compared to size, this is actually one of the machines we have in Nottingham, a molecular beam epitaxy. So it's a very, very large machine compared to the first prototype. So you can see how things, moved very, very quickly. In 1980, this becomes commercially available. These are research machine, practically. So let me now really go to some laser, some devices and show you how this molecular beam epitaxy have helped really tailor or make these quantum lasers really useful. So let me now show you 3 quantum lasers. So the difference between, as you can see, this is the conduction bound, this is the valence bound. The only thing changed between these 3 lasers is the size or the width of the quantum well. So this is very large quantum well, narrower quantum well, and much narrower quantum well. So as I told you before, when you change the size of the quantum well, you can control the energy state inside that quantum well. So you can see here in this white quantum well, I can have this energy. But if I make this quantum well smaller, so I can push this first energy state higher. So now the energy of the photon is much higher than this one. If I make it even smaller, I can push this level even higher. So this is what the light coming from this transition, the combination between this electron and hole, it gives you even higher energy photon. So you can see by changing the size of the quantum well, I can change the wavelength of the quantum dot of the quantum well lasers. So I think the next slide is a bit better. So you can see here by changing the quantum well size. So here, for example, a very large quantum well, 55 angstrom, 46, and so on. But you can see I can tune the laser from 700 nanometers to 900 nanometers by changing only one parameter, not the material, but just the quantum well size. So you can see from 13 angstrom to maybe 55 angstrom. But look here what is very important. By changing the quantum well by only 3 angstrom, you can change this emission quite largely. So can you imagine if you're making, for example, red lasers or some kind of lasers and you must produce them, and you want them in this wavelength, 700 nanometers. So it means that you have to produce these lasers day after day with exactly the same thickness, 13 nanometers. But if you make only one mistake of 3 angstrom, and 3 angstrom is only one layer of gallium arsenide, one layer of arsenic, one layer of gallium, you can shift this wavelength. That means the MBE system is you can control these thicknesses accurately day after day after day. That's why it's very important for mass production, because you want to produce the same device day after day. And you can see the thicknesses are very, very small. If you make a small mistake, that means the laser would not emit at the proper wavelength. So now let me just show you the quantum dots. So the quantum dots is one of, it's very simple to make. I think Professor Kuhlmann has already mentioned the quantum dots. So the quantum dots, people have used different technique of making zero-dimensional system, but I will show you today, this is what we call self-assembled quantum dots. This actually nature help you to do it. So it's very simple. All you have to do is use, for example, 2 semiconductors from the group 3 and the group 5, like indium arsenic, gallium arsenic. And because these two semiconductors have got a different lattice constant, that means the size of the lattice is different. When you try to deposit one larger lattice on top of smaller lattice, so what is happening? You're gonna practically have some strain, and when you go above a certain thickness, that strain becomes like an island. It creates this island. So first, this laser is very, very strained, but when you go above a certain thickness, that strain become an island. So this is like if you wish like a droplet of water on glass. So if you put water on glass, first it's like thin film, and if you put more, then you start having droplets because the surface tension between the water and the glass is different. So this is what we have from quantum dots by this self-assembly technique. It just use two semiconductors with different lattice constant, and this we can have these quantum dots. And then actually you can change the size of these quantum dots. By changing the size of this quantum, you can tune the quantum dot laser to reach wavelengths, from like say 1 micron to 1.6 micron, which is actually in the region of the telecommunication application. As you know, the telecommunication application, they use 1.3 micron and 1.55 micron. So you can actually, by using just the same material system, just by making the quantum dots smaller, you can tune the energy of the emission of the laser to go up to long wavelength without changing the material properties at all. So that's extremely important. Now, let me show you just this is a scanning tiny microscope of these self-assembled quantum dots, which we grew a long time in Nottingham. And you can see these are this island. And you can see sometimes the sizes could be different, but you can control the size distribution, but just give you an idea. But one thing you can notice here, they are, because they are self-assembled, they practically nucleate whatever they like because it's self-assembly. But there are techniques we can actually order them both laterally and vertically by playing some trick to make all these dots really regular. Especially if you want to make quantum computers, you want to access those quantum dots, at the right position. But just to show here, one of the slides to show you how these quantum look like. So let me go back to that first patent. We predicted if you make 1D, 2D, 3D, and didn't even think about 0D. So what is now we can make all these devices, and I'm going to compare their characteristics by making 3D lasers, 2D lasers, and 0D lasers. So here is just showing you here the threshold current of the lasers as a function of time for different structures. This is what you call PN junction or double structure. It's just a 3D diode, a quantum laser diode, and the quantum dot laser diode. So let me just emphasize for those who don't know about the threshold current, that the threshold current is the minimum current you need to make the laser laze. Because you have to pass a certain current before this device lays. And of course, you want that current to be as small as possible. Otherwise, if it's too high, the lifetime of the device will be shorter. So if you look at the 3D lasers, originally grown by different technique, look, it's about 5-6 thousands of amps per square centimeter, that the laser density. And people did whatever they like, they couldn't really reduce. I mean, they could do around 1,000 amps, so it's really high. So in the early 80s, when we started having MBE and making quantum well, you see, and this is the early one where the quantum lasers weren't very good. But look, with function of time, within 10 years' time, you can see the state of the art of these lasers is around 20 amps, 25 amps per square centimeters. So you see, by reducing the size of quantum, the structure, we have gone from nearly 1,000 to 20. Now, when quantum dots came, the structure people can manage to grow the quantum dots. Actually, it was just by accident. So can you see here it's near now about 10, 15 amps per square centimeter. So now they're performing even better than the quantum wire. So you can see this is why the size quantization is very important, as predicted by the density of state. You increase the gain of the device, and therefore you go to, most of the electrons and the hole you create are all contribute to a photon rather than being wasted. Okay, now let me come to the transistor, because of course transistors are very, very important. Let me just show you the classical transistor. This is what you call the field effect transistors. And this is the gate I was telling you about earlier on. So usually what you do, you go to 3 contacts, what you call the source, the gain, and the gate. And here, of course, you go to some gallium arsenide, for example. And then all you do, you pass a current between the source and the drain, and you use this gate practically to control the resistivity, or if you wish, the flow of these electrons in this region. So practically here, you just create some depletion, and you can practically pinch it off completely when you got zero current going through this device. But you can see here the problem with this device. To make it N-type, it means create electrons. For example, using silicon, you have to put silicon in this material, to dope it with silicon. And of course, when the silicon gives you an electrons, to be free, because it's group 3, 5, and silicon group 4, you will have an excess electrons. The electrons will be actually moving in a region where we got a lot of silicon ionized, positively ionized silicon atoms. So we got negative charge and silicon positively charged. So that means when the electron wants to go from this source to the gain, it's going to be slowed down, because you're going to get this positive charge to practically, deflect it. You see, and this is really, if you wish, the mobility of these electrons is very slow, because you got a lot of scattering from these positively charged ions. However, a simple idea came by some people in Japan, and this is what we call modulated doping. So instead of doping the gallium arsenide, where we're going to have this transport of electrons, they dope actually the aluminum gallium arsenide, which has got a high energy gap, with silicon. But you create, of course, here now silicon plus atoms, positive charge, and electrons. But electrons, they never like to stay in a high energy state. So what they do, they go to gallium arsenide. So they move to gallium arsenide because it's a low energy medium. So what has happened, you left the silicon atoms here, positive charged, and you move the electrons here, which is going to be moving into a medium which has got no impurities, or very minimum number of impurities. So that means there would be less scattering, which means that you're going to increase the mobility of the electrons, which means you increase the frequency of these devices. So this is what we call high electron mobility transistors, because now this will operate very, very fast, because there's nothing to stop the electrons or scatter them. So you can see a very simple idea. So this is what we call high electron mobility transistors. And I'll show you some application. But just to show you here what it means. So here, this is the energy profile. So, the positively charged electrons stay in the L gas, and the electrons actually move to this interface. Of course, they cannot go deeper, because you got positive charge electrons, and you got, of course, a Coulombic attraction. So they only stay near the interface. This is what we call them a two-dimensional electron gas. So they are only on the plane near the interface. So here, that's what they call two-dimensional electron gas. So they are in the interface between the L gas and gallium arsenide. So that's extremely important. So here, just to show you, for example, the mobility, of some pure gallium arsenide is only about a few thousand. And then we use this, modulation doping, you can see you can reach millions, 10 of millions mobility. So you increase it by a huge factor. And this mobility, increase the mobility, will means operating at a very high frequency as well. So what is the transistor I use? Of course, most of you guys, or all of you probably use mobile phone. And in every chip, in every mobile phone, you got one of these smartphone, which are made of gallium arsenide, these high electromobility transistors made of gallium arsenide. And they're becoming cheaper and cheaper as we go along. It's a very, very big business, as you know. And these high electromobility transistors are very, very important, because they can work at very high frequency. So they are mass produced. So here this what comes to me as the mass production, commercial production of MB machines. So now, all the research machines, they are either 1 inch or 2 inch substrate. You can only grow on a substrate of 1, 2, or 3 inch. But depending on your applications and where the niche is, you can have bigger and bigger machines. So you can see here one of the biggest machines called MB7000. You can have actually 7 6-inch wafers could grow them at a time. So this equates to around about 24,000 wafers per year per machine. And each wafer you can produce millions and millions of transistors. So you can see, the niches. So you can see here the HEMT transistors. This is what you need to mass produce devices because of the mobile phone, for example. So here you can see why these production machines are extremely important for the mobile phone, because they make these HEMT devices day after day after day. So here, of course, I didn't give you all the applications for the thing. Probably that will be the last slide. But there are many applications. I just choose, for example, one application, for example, lasers. Now let me just show you some molecular beam epitaxy mainly for the solar for photovoltaics using different new material system that we call the dilute 3,5 bismuth nitride. So this just use the 3,5 semiconductors, but you add bismuth or nitrogen to this standard 3,5 semiconductors, and I will explain why. So let's look at this map in here, which is very, very important. It's showing you practically most of the semiconductors used for solar cells. But if we look at the 3,5 semiconductors, it's here. You see, it's all the time increasing. The efficiency of the solar cells is all the time increasing. Look at silicon. Silicon is practically, flattened. So you can see over the last 30, 40 years, silicon hasn't changed much from 16, 17 to about 22, 23% efficiency. But look at the 3,5. It's nearly over 40% efficiency. You see, it's really important, these 3,5 semiconductors. But of course, there are many other new material systems, some oxide and so on. But I would say the best are the 3,5 semiconductors for the 3,5 in terms of efficiency. So let's, Kumar touch on some of those. So of course, this is the spectrum of the solar spectrum. There are many energies in there which you would like to absorb by your device, because when you absorb, you create electrons and holes, and you want to store them. Ideally, you want to absorb all these energies in order to increase the efficiency of the solar cell. But unfortunately, there's not a single material which can absorb every energy in the solar cell. And that's what we call a multi-junction solar cells. So you make a multi-junction, and each material will absorb part of the spectrum. So you can see this one absorb this region here, this green one, this material will absorb this region, and this blue one absorb the visible, for example, visible, infrared, and so on. So that's how we increase the efficiency. And usually these are about 33%. We already got, I think Kumar has already mentioned, some, the 3-junction, which have got 33% and they're in production. But of course, we want to go to the 4th-generation solar cell to increase even further. So this is what the future generation multi-junction solar cell look like. The existing one, what we do, we use, for example, a semiconductor, which have got 0.7 EV, for example, like germanium. Here, like 1.4 EV, I show you as well, so some indium gallium arsenide, and then some 1.8 EV. So this is, the energies we use of some semiconductors to absorb these energies. But as you can see here, there's one energy missing, for example, 1 EV. Okay, so, it's not easy to stack one material over another material, because you need at least that they should match. And one of the major parameters, which is very important, is the lattice constant. So all this material we're going to stack one on top of the other should have similar lattice constant. But if one is bigger than the other, then you're going to have a lot of strain, and then you're going to have a lot of problem. So the challenge has always been how to find a compatible semiconductor to add this 3-junction, which have the similar lattice constant than the 0.7, 1.4, and 1. EV materials. And this 1. EV, which is very important. So the prediction, if you can find this 1 EV material, you should improve the efficiency even higher to 50%. So this is the idea. I'm going to show you what kind of materials. So he's just showing you, for example, the bond gap as a lattice constant. So each time you want to grow a sandwich structure, you have to make sure that the semiconductor have the same lattice constant. Look at here at the germanium, gallium arsenide, aluminum arsenide, they all have the same lattice constant. So you can grow them one on top of the other with no problem at all. So you can see here you go from 0.7 all the way to 2.2 EV. So you can choose this as you like. You see? So here, how to find this 1 EV bond gap material that is lattice match to gallium arsenide. So you can see the 1 EV is here, somewhere around here. And then it's very, very hard to find it. You see? So it's not easy to find it. So this is why we're going to show you how it's possible to do it. So for example, if we take, for example, gallium nitride and here gallium arsenide, for example. So when we add nitrogen to gallium arsenide, we would have expected, like these energies here, that the bond gap should go this way, from gallium arsenide to aluminum to gallium nitride. Should just increase, like here, for example, gallium arsenide, aluminum arsenide, the energy should increase as you increase for example, the aluminum content, go from 0 aluminum to 100%. People were expecting the same thing when you go from gallium arsenide to gallium nitride. If you add nitrogen, 0 nitrogen to 100% nitrogen, so the bond gap should do this. But actually it doesn't. So what it does, the bond gap actually decreases before it increases, because the energy bond gap of gallium arsenide is 1.4 EV. So when you add nitrogen, certain percentage actually goes down before it goes up. So this is how we're going to find this 1 EV material. So next slide. So here you can see, for example, the gallium and arsenic, and you see here nitrogen, and you see the bismuth. These are two important group 5. So what we're trying to do now, we're gonna just trying to replace arsenic either with nitrogen or replace it with bismuth. Okay, and this is what the expected energy bond gap should be. Okay, so this was so many theories, about finding energy gap. Because it was very difficult to grow this material system, for example, gallium arsenide nitrogen or gallium arsenide with bismuth, because you're trying to replace an atom with something either smaller or bigger than it, because bismuth is bigger than arsenic, but nitrogen is smaller than arsenic. So you change the lattice, you create some defects in there. So this is the idea. So what we found that if you take a gallium arsenide with bismuth or gallium arsenide with nitrogen, so the bond gap of gallium arsenide will decrease by 100 MeV for every % of nitrogen. So for example, if you got gallium arsenide 1.4 EV, if you only put 4% of nitrogen, you can decrease by 400 MeV, that you reach 1 EV. And bismuth, it decreases about similar rate, about 90 MeV per % of bismuth. So you don't need a lot of bismuth, you don't need a lot of nitrogen, and hopefully you can keep that lattice constant, practically just using gallium arsenide with a small amount of nitrogen and a small amount of bismuth. And of course, the applications are quite numerous, but I was just concerned on the solar cell 1 EV material for the time being. So here I just show you in terms of theory what does happen. So this is the conduction bond of gallium arsenide. So this is the conduction bond, this is the valence bond, and this is the energy gap. So when you add nitrogen, so what it does, it affects the conduction bond. So the conduction bond split. One of it goes down, one goes up, and that's how we reduce the bond gap. It doesn't affect the valence bond, so that's how we reduce the bond gap. When you put bismuth, actually it's different. Bismuth actually doesn't affect the conduction bond, but affect the valence bond. You see, and then it pushes the valence bond up. So that's how we reduce the bond gap. So by using actually a combination of nitrogen and bismuth, you can tune both the conduction bond and the valence bond to reach 1 EV. So this is what has been going on, and already people are already making this solar cell, 4-junction solar cell, available, and they're reaching about 40-45% of efficiency. So it's been really important. As you can see, the 4-junction is going to change. So they haven't been yet used in some applications, but they're available now to buy these. Of course, they are more expensive than silicon solar cells or the usual 3-5 cells. So in conclusion, I just want to show you the range of commercially available devices made by this molecular beam epitaxy. Okay, so first, of course, you need a machine, you need the wafers because there are all these thin film, and you need the substrate, and of course, you need to fabricate these devices. And the kind of devices you can find in the market, as I showed you, wireless telephony, these HEMT transistors, satellite, for example, solar cells, because you need the high efficiency solar cells in space. you say, because the higher the efficiency, the less material you need, or the smaller the panel, or the weight of the panel to take to space. You can use them, for example, for audio. Your CD, for example, the Blu-ray lasers. You can use them for CD. You can use them for healthcare, lasers, eye surgery, skin healthcare. But as well in cars, you can find light emitting diodes in cars. You can find this, to keep you safe, the distance. They use some planning devices. So there's a huge range of application, using molecular beam epitaxy, because you can make all these devices, quantum devices, quantum dot devices. These are quantum devices, all made from this molecular technique. But of course, MOCVD is as well important for some other devices as well. So sorry. So let me just go to previous. So I hope this just gives you a flavor of what we can do nowadays with this kind of molecular beam epitaxy. As you can see, I didn't, of course, show you the research side of it, but just how this molecular epitaxy was starting in the late 60s as a research machine, how it becomes, a real, commercial system to mass produce these devices, and this wealth of devices which you can make with this technique. So as I said earlier, and the Australian philosopher, he was right. We are in the quantum age because all these devices are based on a quantum phenomena, practically. So I would like to thank you for your attention. I'm happy to take any question you might have. Thank you so much.
Thank you, sir. Thank you very much, sir. Shah, sir, just a sec. Yes, sir.
Professor Henini,
Yes.
thank you. We wish you in person someday in Kashmir, very soon.
I hope so. I hope so.
And Nottingham is looking like very nice. Very, really nice, Nottingham. Really good.
The weather is cooler. I understand. Well, probably in Kashmir it's cooler too. But I know that in some part of India it's very, very hot now.
Yes, yes. Yeah, is this entrance of the university?
No. I think I'm not sure. This is just. I'm not sure how to escape. How can I, move? I'm not sure how to move now to share, because I can't see how I can go back to the normal things, because I never used this. How can I?
So you can go normal. Stop presenting.
Sorry?
Stop sharing.
But how can I go back to, because I can't see. Oops, sorry. I'm not sure where.
What is this actually? What is this?
I think this is Japan. I think this is, just my computer. It updates the wallpaper every time.
Okay.
Expand. How can I? Okay.
We wanted to see the Nottingham.
Okay, so I'm back to So I'm back to here, and I'm gonna stop sharing. So it's stop sharing. Is it? Is that right?
Yes, sir. Yes.
Stop now. Share it.
Okay.
So that you can show that.
So what do you want me to show? Sorry.
No, Nottingham.
I haven't got a picture of Nottingham, but that picture wasn't Nottingham. That was in Japan. I think it's just my computer changed this wallpaper. I didn't see that one before when I started.
Okay.
Being changed this thing every day.
Okay. So we wanted to see the Nottingham. Anyway, we have Professor Henini. Yes. As a formal, I will request my colleague. She has already mentioned your name, already acknowledged your services to NIT Srinagar, and time and again you have acknowledged. So I will request her to say a few words.
So,
Dr. Siman Rabab.
Sir, there are few questions from the participants.
Dr. Siman Rabab.
Sure.
Or Naklesh.
Yes, sir. So before that, we have some questions from the participants.
Will she?
Yeah.
So there is a question from Manik Shaukat. Will there be a limit to which the reduction of size of chipset or transistor, that is semiconductors, will reach in near future?
Let me just see.
Size, sir, size.
Yes, the size. Okay, the size. Okay.
Regarding Moore's law, they are saying.
The Moore's law. If you just think, because all those are silicon integrated circuits. If you think about it, was the minimum size we can reach is a silicon atom, because you can make things smaller and smaller. But the most important thing is when you make these devices smaller and smaller, that means you're going to be closer and closer together. And when they become closer and closer together, one important quantum physics phenomena, the tunneling, becomes so important. That means the electron from one device can tunnel to the other device.
Internet.
And that will become a limiting factor, because tunneling, as you can imagine, the electrons can tunnel through a barrier. So that means when the devices are so close, tunneling becomes very high. The probability of tunneling becomes higher and higher. That means one device can start affecting the other device. So tunneling will be one of the major hurdle for increasing the density of transistors in integrated circuits.
Okay, thank you, sir.
Because remember, those gates, they're already 10 nanometers, and 10 nanometers already tunneling is very important. But of course, the device are a bit bigger. It's just that gate. But if the tones are small, next to each other, very small, tunneling becomes very important.
Okay.
So next
second question is there. Natesh.
Yes, sir. Yeah. How can we control the size of quantum dot nanostructures ranging from 1 to 10 nanometers?
Yes. So the quantum dots, the way we change the size is just by controlling the temperature of the substrate. For example, by the indium arsenide. Of course, you see, and the growth rate. So the lower the growth temperature, the less mobile the indium arsenide is. So therefore, you can start collating, quantum dots together, so they become bigger. So usually we use the growth temperature and the growth rate. So we deposit this indium arsenide very slowly. The rate is very slow. So we control the size by only changing the temperature of the substrate and the growth rate. But as well, we can change as well their shape, by using different tricks, by using different substrate orientation. Because usually we grow this structure on 100 gallium arsenide, but we can grow them on different substrate, different orientation, and we can have pyramids. If we grow them, for example, on the 311 substrate, or we can have them as a lens shape, we can actually play as well on the using different substrates.
Okay, sir. Thank you, sir. Sir, next question goes from Suhail. How can we relate quantum Hall effect with XRD peaks of semiconductor?
Oh, you mean quantum Hall effect with XRD?
Yes, sir.
Because XRD only a quantum Hall effect is a phenomena of quantization, but X-ray only give you the quality of the material. They give you, as you can see, it's just a diffraction pattern of the XRD. I don't know it tells you anything about quantum Hall effect, because the quantum Hall effect is a transport, while XRD is a structural technique to characterize the semiconductors, thicknesses, crystal quality, and so on, thicknesses and so on. It doesn't tell you nothing about the Hall effect, which is transport.
Okay, sir. Okay, sir. Sir, next question is from Akhil. Can quantum dot be used to perform delicate surgeries in human or other animal bodies in near future?
Well, the kind of quantum dots I'm talking about these are solid quantum dots. These are dots, from solid. I think, the gentleman probably, is thinking about, colloidal quantum dots. These are quantum dots suspended into a solution. So those are, there are, of course, those quantum dots are made chemically, and some of them, they are used actually in tracing, for example, cancer cell and so on, so they can be injected and they can tag. So there are actually some quantum dots, but this is not the similar quantum dots, because if you use indium arsenide quantum, they are solid, and arsenic, of course, is poisonous. You see. So those quantum dots which can use in medicine are usually chemically made. This is what you call colloidal. They're suspended suspended in liquid.
Okay, sir.
And usually they operate in the visible.
Okay, sir. So next question is from Nikita. She's asking why gallium arsenide is frequently used in most of the applications.
Yeah. Well, the major difference between gallium arsenide and silicon is the bond gap. The bond gap of gallium arsenide is direct. The bond gap of silicon is indirect. So it doesn't mean silicon doesn't emit light. Gallium arsenide emit light. So gallium arsenide has got, it can both be used in optoelectronics and in high-speed devices because of the energy gap. So this is, and of course the gallium arsenide as well, very important because it can be made very highly resistive. So you can use as substrate to put a lot of devices into gallium arsenide without, interacting. Silicon is very hard to make it semi-insulating. So the disadvantage of silicon is that it has got an indirect gap. So you can't emit light unless you play some tricks. Some people are trying to play some tricks with silicon, to make it emit light. So this is why the reason the gallium arsenide are direct bond gap. You can emit light, lasers, and so on. Most of the 3-5 are direct semiconductors.
Okay, sir. Sir, next question is from Shraddha Mahakal. Do we worry about ohmic contacts at every junction formed by dissimilar semiconductor?
Absolutely. You see, the ohmic contact is extremely important because the voltage you're going to apply across your P and N junction, you want all that voltage to be dropped between the P and N. But if your contact resistance is very high, you're going to drop a voltage as well between the N and the metal contact and the N region, and the metal contact and the P region. So for example, just say if you have to apply only 5 volt to the device, you want all that 5 volt to be between the P and N. But if your 5 volt is between the metal and the N, between the N and the P and the metal, that means you only probably have 3 volts across the P, and it's not good. So it means you need more voltage, So the ohmic contacts are extremely important. They have to be very low resistivity.
Oh, okay, sir.
The contact resistance should be nearly 0 between the metal and the semiconductor.
Okay, sir. So next question is from Abhik Bhabkar. He is asking why molecular beam epitaxy is preferred over pulse laser deposition.
Oh, yes, because of the controllability. You see, first it's safer. You don't have to use that at the target. In pulse laser deposition, you see, you're not sure how uniform the film is going to be. Because you're hitting your target with the laser, where for the MB is the problem. The most important thing is the uniformity across the wafer. You see, as you can see when I show you the MB machines for the mass production, you go 7 6-inch wafers. So that means a big pattern. So the uniformity in terms of composition, thicknesses, doping, it has to be within 0.1% across a huge pattern. So this is the beauty of MB, is this uniformity of the thing. You see, compared to, for example, to pulse laser deposition as well. Because you see, and you don't need to use a target. And of course, these are very high purity materials. All these gallium, aluminum, arsenic, they are 99.9999% pure. That's about 7, 8 nines pure. Compared, for example, to the targets used in pulse laser techniques.
Okay, sir. Sir, next question goes like, how to semiconductor used in nanomaterial particles? I don't get this question.
I don't get that question.
Okay, sir. Let's move on to next one. What are the computational aspects that can be pursued in quantum dots?
Okay, you see the quantum dots, I mean, there's a lot of research of people trying to make this quantum computing using these self-assembled quantum dots. But the problem, as I said, is, in any computer, you have to access the device. You want that device to be 0 or 1, okay? So, up to now, one of the measure using self-assembled quantum dots is the alignment both laterally and vertically, you say. So people are working very, very hard to have that, because remember, self-assembly, the quantum dots are grown wherever they like. It's a natural thing, but you can control them.
Okay,
You say. So, there are a lot of research now where now we got these ordered quantum dots for quantum computing. But for the laser, it doesn't matter where they are. As long as we have them in the active medium, they are emitting photon, that's what it matters. Don't care. But if you use quantum computing because you want to access them one by one, you want to know where they are. If you don't, then it's, so that's what the alignment, both vertical and horizontal, is extremely important.
Okay, sir. Sir, next question is from Anand Stephen. He is asking, what are the basic requirements or equipments for semiconductor research?
Well, semiconductor research is very expensive, and of course, you cannot have everything in your laboratory. You say, so that's why you have to collaborate. You can't have an MBE system in one. I mean, in Nottingham, we are very, very lucky. We had a very large group where we have all these facilities within the department. We have the growth facilities, we have the processing facilities, and we had the characterization facilities. But still, we needed as well some help in terms of SIMS, in terms of transmission electron microscopy. You see help from other groups. So we can't have everything in your lab. So that's why you need to collaborate. And especially now, financial, no one can have everything. So that's why collaboration is extremely important. Not only, because you can have all this equipment in your lab, but if you haven't the expertise, it's a big issue. So I'd rather sometimes collaborate with people who have got the expertise to help with as well to understand the results as well. It's not just because now what's happening, people are more relying on this plug and play. Put a sample in XRD machine, press the button, and give you some numbers. But how to understand those numbers is another story.
Yes, sir.
Say same thing with transmission electron microscopy. Someone can give you an image, but what does it mean? You see, so that's what you need, someone who is really expert. So that's why we cannot you cannot be expert in everything, and that's why collaboration is extremely important.
Yes, sir, indeed. So that was our last question from the participants. Our chat box is filled with appreciation. They are all thanking you, sir, for your nice talk. Now I would request Professor Robab to say a vote of thanks to both of our speakers.
Thank you very much.
Ma'am, please.
It's a very good afternoon to all of you. It's afternoon by Indian time, and we had a wonderful technical session on the first day of this 5-day course. And first of all, I would like to thank our first speaker, Professor J. Kumar, who is a UGC BSR faculty fellow from Anna University. And sir, we have interaction and collaboration with Professor J. Kumar since several years, and he is very keen on getting a memorandum of understanding between two provinces or states of India, that's Jammu and Kashmir and Tamil Nadu, which are from north and south, and this collaboration will benefit faculty and students and researchers from both these states. So for this initiative, we thank Professor J. Kumar sir, and moreover the lecture was excellent. And usually in many talk we don't find interactive audience or participants, but here we have seen that in both the lectures were so illuminating and so engaging that the participants have so many questions which both the erudite scholars answered to their satisfaction. And now I would like to personally thank Professor Mohamed Henini from Nottingham University, who is in charge of Nottingham Nanotechnology and Nanoscience Department. And I hope our participant MSc students and research scholars have immensely benefited from your level of expertise in physics and technology of molecular beam epitaxy. This is evident from the question answer session, and I hope, sir, you have also enjoyed this session. And I personally thank you on behalf of our department that whenever we have contacted you for anything in any program to like spare your valuable time to address us, you have always obliged, sir. So once again, it's a warm, heartfelt gratitude from our department on behalf of our HOD and on behalf of our all colleagues and on behalf of Professor M.A. Shah, who is a dear, dear friend to me. We together organize everything in this department since 20 years. Thank you very much, sir.
Well, thank you very much indeed for your kind words, and it was my pleasure again, at least to see some faces. I've seen Professor Kumar as well in his lectures. I haven't seen him for quite a long time actually, because I used to be a regular visitor to Anna University. This many times. Professor Kumar, actually, we had some collaboration for quite a long time. We have students who visit us at Anna University. And of course, I haven't seen Professor Shah for a long time. We met in Malaysia many years ago, So I hope the situation in India will improve. I know that you are having a very difficult time, and I wish you can stay well and safe. And I hope to meet you in person, whether in the UK or in India soon. I hope the situation will improve for all of us. Especially you guys in India, which is understanding the situation is very dire now. And I just wish you to be well and safe. Thank you very much indeed. And I wish you a very successful meeting, rest of the meeting. If there's any other question or any inquiry, please don't hesitate to contact me.
Okay, sir. Thank you, sir.
Thank you, sir.
Thank you, sir. Thank you.
Thank you very much, sir. Have a nice day.
To see you sometimes in person in Srinagar, and the weather here in Srinagar. India is a temperate country, but Srinagar has similar climates like England.
Yeah. Thank you, Professor Henini. Thank you.
Thank you very much.
We are indebted. We are honored. We are honored.
It's my pleasure. It's my pleasure. It's my pleasure. So have a nice day and a nice weekend as well. And I'll talk to you soon. Bye-bye. Bye-bye.
Bye, sir. Thank you, sir.
Bye. Bye. Thank you. Niklesh, take leave of now. I am tired now.
Okay, sir.
I've been on this chair from 9 a.m.
Thank you, sir. Thank you. Thank you. I request all the participants
Good luck to all of you. Good luck.
Fill in the feedback form that has been shared in the chat box for the attendance. Kindly fill the...
Make this attendance necessary for MSc. Niklesh.
Okay,
Niklesh,
sir.
This attendance is necessary for MSc Physics students.
Okay, sir. For sure.
Make it necessary. Make it. Yeah. Make it.